1.8 millisieverts. Every single day. That is what NASA's own instruments measured striking the human body during the trip to Mars. Not a projection, not a model. A number pulled from a real radiation detector bolted to the Curiosity rover as it crossed the dark between the worlds. For 253 days, the length of that crossing, the dose never paused, never dipped, never gave the body a single hour of true shelter. Run the arithmetic across a full mission, and the total climbs to somewhere between 600 and 1200 millisieverts, enough that NASA's own cancer risk models flag it as a career-ending dose before the first boot has touched the red dirt. And here is the part almost nobody says aloud. Shielding does not fix this. The particles that do the real damage are the nuclei of iron and titanium, moving at a significant fraction of the speed of light, and they pass straight through any wall we currently know how to build. They do not simply strike a cell and stop. They send chemical signals outward into the surrounding healthy tissue, corrupting cells that were never touched at all, doubling the cancer risk beyond what the standard model even predicts. Yet radiation is only the first layer. The deeper story, the one that changes everything, is that the transformation does not begin when you land on Mars. It begins the instant the rocket fires, and it does not stop when you come home. Consider what that number actually represents. 1.8 millisieverts is small enough to sound harmless, the kind of figure you might forget within a sentence. But it is a rate, not a total, and a rate is patient. It accumulates while you sleep. It accumulates while you eat, while you work, while you stare out a small window at an Earth shrinking to a pale blue point behind you. There is no roof thick enough on that journey, no basement to retreat to, no night that turns the exposure off. The dose simply continues, hour after hour, for the entire 253 days of the outbound crossing. Reaching Mars does not end it. On the surface, the same detector measured 0.67 millisieverts every single day, lower than deep space, but never zero. The reason is brutally simple. Mars has no global magnetic field to deflect what is coming, and its atmosphere is far too thin to absorb it. The planet offers almost no shelter at all, so the exposure follows the crew down to the ground and stays with them, patient as ever, through every month of the surface stay. This is the crushing arithmetic of a conjunction-class mission. Such a journey lasts more than 900 days, which means more than a full year spent inside deep space with nowhere to hide. The most dangerous radiation is precisely the kind we cannot stop, not because we lack the will to build a shield, but because the physics simply refuses to cooperate. Shielding works beautifully against one threat: the bursts of particles thrown off by the sun, the solar storms that engineers have learned to anticipate and plan around. It is nearly useless against the other threat, the galactic cosmic rays, the heavy nuclei accelerated to staggering speeds somewhere out among the dead remnants of exploded stars. Build a thicker wall, and you do not stop them. You can even make the problem worse, because a fast nucleus that smashes into shielding can shatter into a spray of new secondary particles. Then there is the discovery that turns a known danger into something stranger. For decades the assumption was simple. A cosmic ray damages the cell it hits, and the cells around it remain safe. That assumption was wrong. Not slightly wrong. Fundamentally wrong. A struck cell does not suffer alone. It broadcasts distress signals into its neighbors, and those neighbors, never touched by a single particle, begin to mutate as though they had been. The damage spreads outward like a rumor through a crowd. NASA's conventional model already predicted greater than a 3% chance of dying of cancer from a single Mars mission. The bystander effect suggests that figure is not the ceiling, it is the floor. A claim like that invites an obvious question. How could anyone possibly know? You cannot measure the cancer that kills a man 30 years after a voyage that has not yet been flown. You cannot stand on a planet no human has ever touched and read its dangers off a dial. So where does a number like 1.8 millisieverts per day actually come from? It did not arrive from a chalkboard. It did not come from a frightened guess about the dark between the worlds. It was carried back to us across the void by a machine no larger than a small car. That machine was the rover Curiosity. It departed Earth on a long curving arc toward Mars, and for the 253 days of its passage through deep space, it carried an instrument with a plain and modest name: the Radiation Assessment Detector. Most of the people who built it simply call it the RAD. The RAD did something no instrument had ever done from inside a vessel crossing the gulf between the planets. It counted, hour after hour, in the sealed dark of the rover's body. It tallied the particles streaming through it. The same particles that would one day stream through the body of any human being seated in that same place. This matters more than it first appears. Every earlier estimate of the radiation between Earth and Mars had been assembled from models, from theory, from detectors parked in orbit close to home. They were educated guesses dressed in mathematics. Curiosity did something different. It carried the question into the actual corridor a crew would one day travel, and it held the question open for the whole long fall toward the red planet. The answer it sent home was not a comfort. During the cruise, the RAD recorded an average dose of 1.8 millisieverts on every single day. Not in bursts, not in occasional spikes. Day after featureless day, the same relentless rain. Then the rover arrived. From August of 2012 through June of 2013, settled onto the floor of its crater, the RAD turned its attention to the surface. There the figure eased to roughly 0.67 millisieverts per day. These were the first direct measurements of radiation ever taken from the surface of another world. For all of human history, we had imagined the dangers of Mars. Now, for the first time, a machine was simply reading them aloud. Notice the shape of those two numbers, because the shape tells a story of its own. The surface dose is lower than the dose in transit, not because Mars shelters you. Mars barely shelters you at all. The relief comes from something simpler and stranger than protection. On the surface, an entire planet sits beneath your feet, and that solid bulk silently swallows every particle that would have come from below. Half the sky is closed, the other half stays wide open, and through that open half, the rain keeps falling, every hour, on every exposed body, with nothing meaningful standing in its way. Now sit with what a number like that actually does to a person over time. A single day of 1.8 millisieverts means almost nothing to a body. You would feel no heat, you would hear no sound. There is no sensation of any kind as these particles pass through your tissues, your organs, the soft coils of your brain. That, precisely, is the danger. The dose does not arrive in one dramatic flash that the body can recognize and react to and mourn. It arrives quietly, invisibly, continuously, accumulating in silence across an entire voyage. And the voyage is not short. A mission to Mars and home again, of the kind engineers call conjunction class, runs more than 900 days. More than one full year of that time is spent in deep space, outside any meaningful protection, with the particles passing through the crew in their silent millions. Think of what that means in human terms. A traveler boards healthy, in the prime of life, and for nearly 3 years the rain never stops. It does not pause while they sleep. It does not pause while they eat or work or speak softly to a planet they can no longer see with the naked eye. NASA's own conventional model, built before anyone fully understood how this kind of damage spreads from cell to cell, already placed the odds of dying of cancer from a single such mission above 3%. 3 in every 100 travelers, condemned by something they would never see and never feel on the day it struck. Hold that figure beside an ordinary risk, and its weight comes into focus. We accept tiny fractions of a percent as the price of crossing a city or boarding a plane. Here the number is not a fraction, it is 3 full chances in 100, and it predates the deeper understanding already described, the discovery that struck cells whisper damage into their untouched neighbours. The model that produced 3% did not yet account for that whisper. The honest reading is that the true danger sits somewhere above the figure we can confidently name, in territory the early models never mapped. To understand why no engineer can simply build that danger away, you have to understand what these particles actually are. And to understand that, you have to follow them backward, away from Mars, away from the Sun, out past the edge of everything familiar. They are not born in our solar system. They are not pieces of sunlight or fragments of solar wind. The galactic cosmic rays are the wreckage of dead stars. When a massive star reaches the end of its life and detonates as a supernova, the shockwave of that explosion races outward and accelerates whatever it touches to a fraction of the speed of light. What it touches, among other things, are the bare nuclei of heavy atoms. Iron, titanium, stripped of every electron, naked and charged and moving almost as fast as light itself. Consider what kind of bullet that makes. A particle from the sun is dangerous, but it is light, and it can be stopped. A galactic iron nucleus is something else entirely. It carries an energy that a solar particle cannot begin to approach, and it carries the mass of a whole heavy atom behind that energy. When it strikes living tissue, it does not gently deposit a little warmth. It tears a microscopic tunnel straight through, smashing the delicate machinery of cells along its entire path, leaving a trail of wreckage that the body must somehow find and repair before that wreckage becomes a tumor. Now remember how many of them there are. Remember that they fall continuously from every direction for 900 days. These particles were forged in the deaths of stars that exploded before the sun was even born. That is the strange and humbling fact buried inside the radiation report. The thing most likely to give a Mars astronaut a fatal cancer is older than the sun, older than the Earth, older than the very atoms that make up the body it will eventually kill. It has been traveling across the galaxy for longer than our world has existed, and its destination, by sheer cosmic accident, turns out to be a single cell inside a single traveler somewhere on the road between two planets. This is why the danger cannot be engineered into silence the way a solar storm can. The sun is the threat we have learned to survive. When the sun convulses and hurls out its storm of charged particles, a crew can retreat into a sheltered inner room and ride out the worst of it, because that kind of radiation can be blocked. The galactic rays answer to no such defense. They are too fast, too heavy, too charged, and they arrive not in a brief storm that passes, but in a steady, unending drizzle that no schedule can predict and no shelter can outlast. You cannot wait for it to stop. It does not stop. It has not stopped in billions of years. And Mars itself offers no rescue. Here on Earth, two invisible guardians stand between every living thing and that rain from the dead stars. A deep magnetic field wraps the planet and turns the charged particles aside. A thick blanket of atmosphere absorbs much of what gets through. We walk beneath both of them every day of our lives and never feel them working, never thank them, never even notice they are there. Mars has neither. It carries no global magnetic field to deflect the incoming nuclei. Its atmosphere is a thin and ragged thing, far too sparse to absorb the heavy rays. A traveler standing on that surface stands almost naked beneath the open galaxy, shielded only by the planet at their feet and by nothing at all above their head. So the exposure does not come in a single chapter that a crew might brace for and then put behind them. It comes in three. There is the outbound transit, months in deep space with the full rain falling. There is the surface stay, the dose eased but never stopped, accumulating soul after soul while the crew works and waits for the planets to align for home. And then there is the return transit, months more in the open dark, the body absorbing what it cannot refuse, on a voyage from which there is no early exit and no turning back. At no point in the entire mission does the traveler step out of the rain. There is no dry place. There is no still hour. From the moment the spacecraft leaves the protection of Earth to the moment it returns, the particles are always passing through, always counting, always leaving their faint tunnels of damage in tissue, that may not reveal what was done to it for years. And radiation, as it turns out, is only the first of the changes. It is the one we can measure most cleanly, the one a machine the size of a car could read aloud from another planet. The others are quieter. They begin not in the cells, but in the architecture of the body itself. Yet even radiation, the change we claim to understand best, refuses to stay where we file it. We speak of it as cancer risk, as a percentage, as a single number printed on a chart. The deeper truth is that the same particles reach all the way into the architecture of the body, into the very instructions that let it rebuild itself. A living thing is not a fixed structure. It is a structure under constant reconstruction, torn down and raised again cell by cell, hour after hour, for as long as it lives. Corrupt the blueprint that guides that rebuilding, and the body still stands for a while. It simply begins to rise a little crooked, in ways no one can see. This is why the harm cannot be felt while it is being done. There is no heat, no sound, no sting to warn the traveller that a strand of code has just been cut. The damage is invisible at the moment of impact and silent for years afterward, ripening on a clock the body cannot read. Not because the damage is small, the damage is real, and much of it is permanent, but because the consequences surface so slowly, appearing as illness a decade or two later, long after the particle that caused it has passed out the far side of the body and back into the dark between the stars. In 2017, the physicist Francis Cucinotta, working at the University of Nevada in Las Vegas, described why the official estimates may be too gentle. A cell struck directly, his work showed, does not suffer alone. It sends chemical signals to its untouched neighbours, and those neighbours, never hit by anything at all, begin to mutate as though they had been. The number of cells harmed is therefore far larger than the number of cells the particles actually reach. By this accounting, the danger does not rise a little. It roughly doubles beyond what the conventional model had assumed. The conventional model was already severe. NASA's own figures, even before this newer understanding, placed the chance of dying of cancer from the radiation of a single Mars mission at greater than 3%. 3 in every 100 travellers, killed not by any accident of the voyage, but by the slow arithmetic of particles gathered along the way. Cucinotta's work suggests that 3% is a floor and not a ceiling. The honest answer is that no one yet knows the true figure, because no human being has ever spent 900 days and more inside that rain, and then lived long enough afterward for the final count to be taken. Set the whole journey end to end, and the true scale appears. The outbound crossing alone takes the better part of a year, every day of it spent in the full, unfiltered stream of deep space. The surface stay adds many months more, the crew waiting for Earth and Mars to drift back into the narrow window that makes a return even possible. Then comes the long fall home, months again in the open dark. This is a passage counted in years, not in days, and across every hour of it the particles keep their steady toll. There is no leg of the trip the body is allowed to sit out. Shielding offers only the cruelest kind of partial comfort. It can blunt the sudden floods of particles thrown out by a solar storm, the violent surges that swell and fade within hours. It can do almost nothing against the galactic cosmic rays, the iron and the titanium nuclei flung outward by exploding stars and accelerated to within a breath of the speed of light. A wall thick enough to stop them would weigh more than any rocket could ever carry off the ground. So the engineers protect the crew from the storm they can see and leave them open to the rain they cannot. Mars itself offers no sanctuary worthy of the name. The planet has no global magnetic field to turn the particles aside, none of the invisible shield that wraps the Earth and deflects most of what the Sun and the galaxy hurl toward us. Its atmosphere is a thin and ragged remnant, far too sparse to absorb what rains down from above. On the surface the dose drops, but it never reaches zero. Curiosity, sitting in the rust-coloured dust of Gale Crater, measured close to 2/3 of a millisievert on Martian ground, each day, every day, for as long as a crew would have to remain. The ground gives shelter from below. The entire sky stays open overhead. To appreciate how relentless this truly is, consider that no posture and no schedule escapes it. A traveler cannot work the night shift to dodge the radiation, because there is no night the particles respect. A crew cannot ration the dose the way they ration water and air, because the dose is not theirs to ration. It arrives whether they sleep or wake, whether they labor or rest, whether they are calm or afraid. The body simply takes it in, and takes it in, and keeps taking it in, and the only ledger that records the running total is written invisibly inside the cells. If you could shrink yourself to the size of a molecule and stand inside a single living cell at the instant one of these heavy nuclei arrived, you would not see a gentle glow. You would see a line of devastation drawn faster than thought, a tunnel of shattered bonds punched clean through everything in its path before the cell had any chance to flinch. Then, nothing. The particle is already gone, already racing on through the body and out the far side, indifferent to the wreckage it left in a stranger's chromosome. The cell must now decide, with no awareness of what just struck it, whether to mend the break, ignore it, or quietly carry the error forward into every copy it ever makes. Here is the heart of why the title of this journey is not an exaggeration. A broken bone can knit, a torn muscle can heal, a cut chromosome, repaired wrongly, becomes part of the permanent record of the cell, copied faithfully into its descendants for the rest of a life. The radiation does not injure the traveler the way a fall or a fever does, as an event to be recovered from and forgotten. It edits the traveler, line by line, in a text that has no eraser. Some of those edits will mean nothing at all. A few of them, decades later, will mean everything. This is the first and clearest of the marks the journey leaves on a person. We can measure it only because a machine the size of a small car carried an instrument across the emptiness and counted for us, day after day, and sent the tally home. The radiation is legible. It can be modelled, estimated, argued over in percentages and reports. The changes that follow are harder to see, and in some ways harder to bear, because they need no supernova and no stream of heavy ions to begin. They ask only for the absence of something we have never once lived without. Not a poison added to the body, but a force quietly subtracted from it. That force is gravity, the steady downward pull that every bone and muscle and inner ear has expected without pause since the first cell divided in an ancient sea. The radiation can be counted, and it is still the change we understand best of all the things this voyage does to a person. Everything that comes after it begins in the same instant. The moment the engines fall silent, the weight slips away, and the body is asked, for the first time in the entire history of our species, to learn how to live without the ground that built it. The body's first answer to that subtraction does not come from the muscles you can flex, or the heart you can feel beating against your ribs. It comes from somewhere deeper, from the one structure you were taught to think of as permanent. Your skeleton is not the dead scaffolding most people picture when they imagine bone. It is living tissue, dissolved and rebuilt and dissolved again across the whole length of your life, and the single instruction it has always obeyed is the pull of the ground beneath you. Take that pull away, and the skeleton begins to wait for a signal that never arrives. This is the core mechanism of what a long voyage does to a human being. It is also the change we can measure most precisely of all. On Earth, bone lives in a constant negotiation with gravity. Every step you take, every time you rise from a chair, the weight of your own body travels down through your legs and your spine, and your bones read that pressure as a reason to stay strong. Certain cells tear old bone away, other cells lay fresh bone down in its place. Under the steady load of one full Earth gravity, the two processes hold a rough and lifelong balance, and the skeleton you carry stays close to the skeleton you need. In the absence of weight, that balance does not stop. It simply tips. The tearing continues at its usual pace, the rebuilding falls behind, and bone begins to leave the body faster than it can return. The rate of that loss is not subtle. Astronauts in orbit shed between 1 and 2% of their bone mineral density every single month. Consider what that figure means set against the slow arithmetic of ordinary life. A healthy older adult on the ground might lose roughly 1% of their bone across an entire year, and we give that loss a gentle name. We call it aging. In space, the same loss can arrive inside a single month, and then again the next month, and again the month after that, without interruption. This is not a slow crisis that gathers across decades. It is aging compressed and accelerated, run at a speed the human skeleton was never built to endure, not because microgravity is poisonous to bone, but because bone was always a conversation with the ground, and in space there is suddenly nothing left to answer. To appreciate how disturbing this becomes, you have to stretch that monthly loss across the real length of a journey to Mars. In the year 2020, a team of researchers led by a scientist named Axbay, working across NASA's Ames Research Center in California and Stanford University, set out to do exactly that. They published their findings in the journal PLOS One. Their method was not a guess and not a worry. It was a calculation built from decades of measured bone loss in real astronauts, projected forward onto the two kinds of mission that could actually carry people to Mars and home again. The first kind is the faster mission, the opposition-class voyage that lasts somewhere between 400 and 600 days. For that journey, the model predicted that 62% of the crew would develop osteopenia, the early thinning of bone that comes before true disease, with losses in the neck of the thigh bone running from 15.6 to 22%. The second kind is the longer mission, the conjunction-class voyage that runs past 1,000 days. For that journey, the number was not a fraction or a likelihood, it was a certainty. 100% of the crew would develop osteopenia. A third of them would cross into the danger zone for full osteoporosis. And the loss in that same span of thigh bone would reach 32.4 to 36.8%. Hold that final number still for a moment, because it deserves to be felt rather than merely heard. More than a third of the bone gone from the place where it matters most. The femoral neck is the narrow bridge of bone at the very top of your thigh, the slender column where the long bone of your leg turns and meets the socket of your hip. It is the exact spot that snaps in elderly people when they fall, the fracture that so often marks the end of an independent life. The study found that 79% of the cases it analysed would fall past NASA's own line of acceptable risk, a measurement called a T-score, set at -2. That score is simply a way of grading how far a person's bone has dropped below the strong baseline of a healthy young adult. -2 is the number at which the agency itself says the risk is no longer permissible. 4 out of every 5 simulated travelers crossed it. So the question that matters is not only how much bone is lost on the way to Mars, the question is whether any of it comes back once the traveler is home. Here is where the most quietly devastating evidence appears, and it does not come from a simulation at all. It comes from the bodies of people who have already flown. In the year 2022, researchers published a study in the journal Scientific Reports that followed 17 real astronauts, 14 men and 3 women, with an average age of just under 47. The scientists scanned their skeletons before flight, after landing, and then again across a full year back on the ground. They were not asking how much bone was lost. They were asking the harder thing. They were asking whether the loss could be undone. The answer was that for many of them, it could not. More than half of the astronauts, 9 of the 17, showed incomplete recovery of bone density in the tibia, the large weight-bearing bone of the lower leg, even after 12 full months of living again under Earth's gravity. The split was sharp, and it tracked the length of the mission. Astronauts who had flown for longer than 6 months carried a median deficit of -3.9%. Those who had flown for shorter stretches carried a deficit of only -0.4%, a difference that all but vanishes. The longer you stay away from gravity, the more of yourself you leave behind, and the less of it your body knows how to reclaim. What troubled the researchers most was not the amount of bone still missing. It was where the recovery stopped. The thickness and the internal architecture of the bone, the fine trabecular structure deep inside, did not return to what it had been, and the recovery did not slow gradually towards some eventual finish line. It plateaued. Between the 6th month and the 12th month back on Earth, the rebuilding simply leveled off and stayed there, as though the body had quietly decided that this diminished skeleton was the new shape it would keep. Not a temporary injury healing on a long timeline, something closer to a permanent settlement, signed without the traveller's consent. To understand why that distinction is so heavy, you have to understand what the trabecular structure actually is. Picture the inside of a bone not as a solid rod, but as a dense honeycomb, a three-dimensional lattice of tiny struts and crossbeams that gives the bone its lightness and its astonishing strength. That lattice is what lets a structure as thin as your hip carry the entire weight of your body for 80 years. When bone is lost slowly under disease on Earth, the struts of that lattice thin and break and are not replaced, and once a crossbeam is gone, the body has no blueprint to rebuild it in the same place. The broader research on long missions reaches the same grim conclusion. Bone density itself may take up to 3 years to recover, if it recovers at all. The microarchitecture, the internal scaffolding that gives bone its true strength, may never fully come back. Now bring that finding out of the laboratory and into a body, because this is not a chart, it is a person. Imagine an astronaut who has spent the better part of 3 years away from Earth, more than 1,000 days in which the load on their bones has been a fraction of what they were born to carry. They have crossed the void, walked on another world, and crossed the void again. And somewhere in that long absence, without pain and without warning, the lattice inside their hips and spine has quietly thinned past the point of full return. They feel nothing. There is no ache that announces it, no moment of injury to remember. The skeleton does not send pain when it loses its strength. It simply becomes more fragile in silence, until the day a force it would once have shrugged off becomes the force that breaks it. This is the cruelty hidden inside the core mechanism. The radiation of the previous stretch of this story at least leaves a record you can read, a tally of particles and a percentage of risk. Bone loss leaves no such warning to the person carrying it. It is felt only in absence, discovered only in the scan, or worse, in the fall. And the traveller returning from Mars does not lose this bone under simple conditions. They lose it across a journey built from more than one kind of low gravity, in stages, each one taking its own portion before the next begins. Consider what that journey asks of a single human skeleton, stage by stage, with no true pause between the stages in which to heal. There are 4 such stages, and each one takes its portion before handing the body to the next. None of them gives anything back. None of them waits for the body to be ready. The first stage is the long outbound fall, months of weightlessness as the spacecraft drifts toward a distant point of rust-colored light, and in that weightlessness, the skeleton surrenders 1 to 2% of its mineral density with every passing month. The reason is almost insultingly simple. Bone is an honest tissue. It keeps precisely as much of itself as the forces around it require, and not one fraction more. On Earth, every step, every time you rise from a chair, every moment you stand against the planet's pull, you are sending a signal down through your bones that says this strength is still needed. In the absence of weight, that signal goes quiet. The body, hearing nothing, concludes that the strength is no longer being used. And so it begins to dismantle what it can no longer justify carrying, not out of malfunction, out of obedience to a rule that served us perfectly for every ancestor who ever lived on the ground. Then comes the second stage. The traveller descends to the surface of Mars and feels, for the first time in months, something pressing them gently toward a floor. It would be easy to imagine this as rescue. It is not. The gravity at the Martian surface is roughly 38% of the gravity here on Earth. A person who weighed 180 pounds standing in their kitchen would feel as though they weighed closer to 68 pounds standing on Mars. Their own steps would carry a strange floating lightness, every stride longer than it should be, every object easier to lift than instinct expects. And this is the trap hidden inside the relief. It is gravity, yes, real and constant and downward. But it is a thin gravity, a partial gravity, far too weak to undo what the transit has already taken. The skeleton is no longer in free fall, it is simply declining more slowly, not healing, not rebuilding, merely losing ground at a gentler rate, for month after month after month, on a world that cannot give it back what a full Earth gravity once provided. Then the third stage arrives, and it is the second stage in reverse. The crew lifts off from Mars and re-enters the long weightless dark for the return voyage home, another 6 to 9 months suspended in nothing. The brief partial gravity of the surface is gone. The slow monthly loss resumes its quiet work on a frame that was already weaker than the one that left Earth. By now the skeleton has been thinned and re-thinned across a span longer than most people spend at any single job in a year of their lives. And it has done all of this without a single sensation to mark its passing. The fourth stage is the one no rehearsal can soften. The capsule strikes the upper atmosphere of Earth, and the planet seizes the returning body and pulls it down at full strength. One gravity. The same force every human alive treats as nothing, as the simple background condition of standing up. But the body arriving home has not felt a full gravity in more than 2 years. The bones that meet that force are not the bones that left. This is the moment the entire long arithmetic of the journey comes due, all at once, on a skeleton that has been quietly unmade in 4 successive stages and given no chance between any of them to recover. Consider what this means for the person inside that body. On Earth, a stumble is forgettable. You catch yourself. You brace against a wall. Your hip absorbs the impact and you walk on, perhaps with a bruise, almost never with a thought. But a femoral neck that has lost roughly 1/3 of its mineral density does not absorb a stumble the way a healthy one does. The margin that once stood between an ordinary misstep and a serious break has been spent, slowly, silently, across the journey. A force the traveller would have shrugged off without noticing before they left can become, on the day they return, the force that fractures them. And the danger is not only the break itself, it is where the break would happen, and when. Imagine a fracture occurring not after landing but during the mission, on the surface of Mars or in the transit between worlds. There is no hospital waiting, there is no surgical team standing by. Emergency surgery in microgravity is extraordinarily difficult, a problem so unsolved that a single serious break could threaten not just one crew member, but the survival of the entire mission. Blood does not pool where it should. Instruments and fluids do not stay where they are set down. The body that needs the operation is the same body that has spent months losing the very tissue now broken. A fracture on Earth is an inconvenience and a cast. A fracture on the way to Mars is a crisis with no clean solution, hundreds of millions of miles from the nearest operating room. And even for those who never fall, who return whole and unbroken, the skeleton does not simply forgive the journey and reset. The loss does not run only through the dense outer shell of the bone. It runs deep into the trabecular interior, the fine internal scaffolding, the delicate honeycomb of struts and beams that gives bone its true strength from the inside. That inner architecture can be thinned and severed in ways the body cannot reliably rebuild. Even after the slow years of recovery on Earth, even after the mineral density itself climbs part way back, the internal scaffolding may never return to what it was. The strength can be partially restored. The architecture that carried that strength may be lost for good. A traveller can come home, regain weight in their bones, pass a scan that looks almost normal, and still carry inside them a skeleton quietly rebuilt to a weaker blueprint than the one they were born with. This is the core mechanism in its full and patient cruelty. Radiation, in the chapter before this one, at least announces itself as a number, a dose, a counted percentage of risk you can hold in your mind. Bone loss announces nothing. It is felt only in absence. It is the strength that is no longer there when a force finally arrives to test it. It is measured not by what the traveller feels, but by what their body can no longer do, discovered in a scan, or in a fall, or in a fracture that should never have happened. The skeleton is the frame on which everything else is hung, the quiet architecture that holds a human upright against a world, and the journey to Mars rewrites that architecture in silence, stage by stage, taking its portion at every step of the way out and every step of the way back. And yet the skeleton is only the frame. It is the scaffold, the structure, the still and load-bearing part of what a human being is. It does not think, it does not remember, it does not dream or decide or fear. The frame can be measured, charted, and at least partly understood, its losses written into the honest language of percentages and density. But the journey does not stop at the frame. It reaches inward, past the bone, past the marrow, into the soft and electric tissue that the skeleton exists to protect, into the one organ that makes the traveller who they are. And there, in the place where the self is kept, the changes are stranger still. The brain is not anchored the way the bones are. It floats. It rests inside the skull, suspended in a thin bath of fluid, soft tissue, with roughly the consistency of set custard, held in place by delicate membranes and the gentle pressure of the cushion around it. On Earth, gravity pulls that whole arrangement downward, settling the brain a little lower in its case, draining fluid away from the head and down through the body in a steady, lifelong rhythm that the tissue has never once been without. This is the silent condition of every thought you have ever had. Your mind has always worked while being pulled gently toward the ground. Take that pull away, and the arrangement does not simply float in place. It shifts. Fluid that should drain downward instead pulls upward toward the skull. The brain drifts slightly higher inside its bath, pressing where it never pressed before. And the fluid-filled cavities at the center of the brain, the hollow spaces called the ventricles, begin to change their shape and their size, not because the brain is injured, not because anything has struck it or starved it, but because the one constant force that organized its fluids for a lifetime has quietly been switched off. For a long time, nobody could see this clearly. The changes are buried deep inside a living skull, invisible from the outside, too subtle to feel as they happen. To measure them, you need to photograph the same brain before it leaves Earth and again after it returns, and you need to do this for many brains, carefully across years. That is exactly what was done. In 2019, a researcher named Jessica K. Lee, working with NASA and the University of Texas Medical Branch in Galveston, published a study in the journal JAMA Neurology. The data had been gathered patiently between 2010 and 2015. The brains belonged to 15 astronauts, each one scanned by magnetic resonance imaging before flight, and again after, each scan compared against the last. What the scans revealed was not dramatic to the eye. It was quiet, and it was structural, and that is precisely what made it disturbing. The white matter of the brain had changed. White matter is the deep wiring, the dense bundles of insulated fibers that carry signals from one region to another, the cabling that lets distant parts of the mind speak to each other in fractions of a second. In the returning astronauts, that wiring showed measurable alteration across some of its most important pathways. The corpus callosum, the great bridge of fibers joining the left and right halves of the brain. The corticospinal tract, the highway that carries the command to move from the brain down toward the body. The cerebellar peduncles, the stalks that connect the balance center to everything else. The size of the change was small in number and enormous in meaning. Across these regions, the white matter shifted by somewhere between 0.75% and 1.25%. A fraction, a whisper, the kind of number that sounds like nothing at all until you ask what it should be compared against. So compare it. A healthy human brain ages, slowly, across decades, and as it ages its white matter changes too, drifting at a rate of less than 1% in a full year of ordinary life. The astronauts had moved roughly twice that far. Their wiring had shifted at about double the pace of normal aging, not across a decade, not across a year of birthdays, but across a single mission. Consider what this means. A person climbs into a vehicle in good health, spends a matter of months away from the ground, and steps out with a brain whose deep architecture has aged at twice its natural speed while they were gone. The body kept its years. The deep wiring quietly spent more than its share. There was a second measurement layered beneath the first, and it described where the brain's water had gone. Spaceflight redistributes the fluid inside the skull, and the study traced that redistribution moving through the tissue itself, a shifting of free water across the brain's regions of somewhere between 2.5% and 4%. This is not the brain thinking differently. It is the physical medium of thought rearranging itself, the fluid balance that the tissue had held steady for a lifetime, quietly finding a new and unfamiliar equilibrium in the absence of weight. And here is the part that lifts this out of the realm of pure abstraction. These changes did not stay hidden inside the numbers. They surfaced in the people. The white matter alterations correlated with measurable decline in balance and with altered reaction times after the astronauts came home. The wiring had changed, and the changes could be seen in how steadily a returning crew member could stand, in how quickly they could respond to a signal that asked them to move. The deep cabling that carries balance and command had been subtly rerouted by months without gravity, and the body wore the difference openly, in the plainest possible terms, in standing, in catching oneself, in the speed of a reflex. This distinction matters enormously because it tells us the alteration is not cosmetic. A brain is not a photograph to be admired for its symmetry. It is a working instrument, and when the instrument's deep structure shifts, the work it does shifts with it. The astronauts in that study were not damaged in any obvious or visible way. They returned, they walked, they recovered. But something measurable had moved inside them, in the very tissue where balance and timing and the sense of one's own body are computed. And it had moved further in months than a still and grounded life would have moved in years. Now hold that finding still for a moment, because a second study, published several years later, found something that runs even deeper than the wiring. It found that the spaces inside the brain do not simply change while you are in flight. They change, and then they refuse to change all the way back. In 2023, a study appeared in the journal Scientific Reports, built from a larger group than the white matter work. 30 participants in all, each followed through multiple sessions inside the magnetic resonance scanner, their brains charted before flight, soon after return, and again across the long months that followed. The focus this time was on those hollow central cavities, the ventricles, the fluid-filled chambers at the core of the brain, and the finding was stark in a way that earlier work had only hinted at. After 6 months in space, the ventricles had grown, not by a sliver, by as much as 25% of their volume. Picture that proportion at human scale. Imagine a familiar hollow space, a room you know well, and imagine returning to it to find it had silently expanded by a quarter while you were away, the walls pushed outward, the volumes swollen, everything around the edges quietly displaced to make room. That is the order of change measured at the center of a living brain after half a year without gravity. The cavities that hold the brain's inner fluid had widened, and the soft tissue around them had been pressed gently outward to accommodate the swell. A brain can tolerate this. Tissue is more forgiving than bone, and the body has a remarkable patience for slow repair. But repair is exactly where this study delivered its hardest sentence. The ventricles did not snap back. By 6 to 7 months after returning to Earth, after the better part of a year on solid ground, the expanded cavities had recovered only somewhere between 55 and 64% of the way toward their original size, more than half the journey home, and still a third or more of the swelling remained, holding its ground inside the skull long after the mission was over, long after the astronaut had walked back into ordinary life. And there is one more thread in that finding, and it is the thread that reaches forward toward Mars. The researchers looked at astronauts who had flown more than once, who had returned to space within roughly 3 years of an earlier mission. In those crew members, the ventricles expanded again. The renewed flight produced renewed swelling, as though the cavities had not yet recovered the full elasticity to expand and contract cleanly a second time. The reading that emerged was sobering and specific. The ventricles did not appear to regain their complete elasticity for something close to 3 full years after a single spaceflight. 3 years for the inner architecture of the brain to finish settling back toward what it had been before. Set that timeline beside the timeline of Mars. A conjunction-class journey to Mars and back is not measured in weeks. It runs beyond 900 days, more than a single uninterrupted year spent away from the ground. And through every one of those days, the brain would be living inside the very condition that drives this change. There would be no 6-month limit on the exposure. There would be no early return to gravity to begin the slow work of settling the fluids back into place. The traveller would arrive home, after all of it, while the deep structure of their own mind was still rearranged, still mid-recovery, the cavities still swollen and the wiring still shifted, with the better part of those 3 patient years of healing not yet even begun. This is the unsettling arithmetic of the brain in transit. The bone, at least, loses its mass in a way that can be charted in clean percentages and slowly rebuilt. But the organ that does the charting, the tissue that holds the self together and decides what any of it means, is changed in a slower and more stubborn way, on a clock that does not bend to fit a mission. The skeleton bends the frame. This bends the thing the frame was built to carry. And the bending goes deeper than the hollow spaces alone. Beneath those fluid cavities, threaded through the brain like the cabling of a vast and silent city, runs the white matter. These are the long fibers that carry signal from one region to another, the wiring that lets the separate parts of the mind speak to each other. For a long time it was assumed that this deep architecture was stable. Whatever weightlessness did to an astronaut, the thinking went, it did to the surface and left the foundation untouched. That assumption did not survive close measurement. In 2019, a team led by Jessica K. Lee, working with NASA and the University of Texas Medical Branch, published the results of a study that had quietly gathered data on 15 astronauts between 2010 and 2015. They had taken detailed scans of the same brains before flight and again after flight. Not impressions, not estimates. The same wiring, measured against itself across the gap of an entire mission. It is one thing to suspect that something has changed. It is another to lay the 2 images side by side and watch the change resolve into numbers. What they found was a quiet rewriting of the deep structure. White matter changes of roughly 0.75% to 1, and 0.25% appeared across some of the most fundamental pathways in the human brain. The corpus callosum, the great bridge that links the 2 hemispheres. The corticospinal tract, the cable that carries the brain's intentions down toward the muscles. The cerebellar peduncles, the connections that feed balance and coordination. These are not minor side roads in the architecture of a mind. They are the main lines, and the rate of that change is the part that lingers. On Earth, in the ordinary course of growing older, the white matter of the brain shifts by something under 1% across a full year. The astronauts showed changes at roughly twice that rate. A single mission, measured in months, had moved the deep wiring of the brain by something closer to what an entire year of ordinary aging would do. Not the slow drift of a life lived on solid ground, the accelerated drift of a body suspended somewhere it was never built to be. There was a second signature hidden in the same scans, subtler and stranger. The water in the brain had moved. Free water, the fluid that sits between and around the brain's tissue, had redistributed itself by between 2.5% and 4% across different regions. The brain had not simply swelled or shrunk in volume, it had rearranged where its own fluid settled, finding a new and unfamiliar balance in the absence of the steady downward pull it had felt for every previous second of its existence. Imagine the sea inside the skull, sloshed by gravity all your life, suddenly told that down no longer means anything, and slowly choosing a new place to rest. And here is where the numbers stop being abstract. The changes in that white matter did not stay locked inside the scan. They tracked, measurably, with how the astronauts moved and how quickly they could respond. Where the deep wiring had shifted most, balance declined. Reaction times changed. The body that came home was a little slower to catch itself, a little less certain on its feet, and the cause was not only in the wasted muscle or the confused inner ear, it was written into the cabling itself. The signal still travelled, it simply travelled along a brain that was no longer quite the brain that had left. Consider what this means for a traveller bound for Mars. If a 6-month stay aboard a station circling close to Earth can move the deep wiring of the brain by something like a year of aging, then a journey of 900 days and more does not simply repeat that insult a single time. It extends it across the entire arc of the mission. The outbound transit, the long surface stay, the transit home. Through every one of those phases, the white matter would keep drifting, the free water keep resettling, the great bridges between the hemispheres keep being quietly rewritten, with no pause in gravity anywhere along the way long enough to halt it. And the cruelty of the timing repeats here exactly as it did with the swollen cavities. The traveller would step out onto Earth with both signatures present at once. Ventricles still expanded and not yet returned to their old shape. White matter already shifted along the very lines that govern balance, movement, and the speed of thought. The faculties a returning astronaut most desperately needs in the fragile first hours back under full gravity, the steadiness, the quick correction, the sure footing, are precisely the faculties that the journey has most quietly eroded. Picture the moment of arrival. A person who has not felt the full weight of their own body in the better part of 3 years. Lowered from the capsule, unable to stand without hands to hold them. The inner ear insisting that the floor is sliding when it is perfectly still. And underneath that visible struggle, invisible to anyone watching, a brain whose balance pathways have been thinned and whose reaction times have lengthened, being asked to perform the single most demanding act of coordination it has faced in years. Not from weakness of will, not from any failure of training, from a structural change in the very tissue that does the willing and the training both. This is the disquieting truth that the brain in space reveals. The mind is not a passenger riding safely inside the body, sealed away from whatever the body endures. It is tissue. It is wiring and fluid and pressure, as subject to the loss of gravity as any bone or muscle, and slower than either of them to find its way home. We speak of the spirit as something separate, something that would carry on unchanged no matter what the journey demanded of the flesh. The scans say otherwise. The scans say the instrument of the self is made of the same vulnerable stuff as everything else, and that it bends, and it does find its way back, mostly given enough time. The ventricles deflate by degrees. The white matter, presumably, settles towards something like its old arrangement, but the clock on that recovery is measured in years, not months, and a mission to Mars does not grant years of stillness between the leaving and the returning. It grants the long going out. It grants the long coming back. And it asks the brain to absorb the full weight of both before the first has begun to finish healing. There is no window in that itinerary wide enough for the mind to rest and reset before the next demand arrives. And yet the brain and the bone, for all their slow and stubborn changes, share one small mercy between them. They can be seen. A scan can find the swollen cavity and trace the shifted pathway. A measurement can chart the thinning skeleton down to the last fraction of a percent. The damage announces itself in images and in numbers, in something a physician can hold up to the light and point to. It is grim, but it is legible. You can at least know the shape of what you have lost. There is, however, a layer beneath even this, a layer that casts no shadow on any scan, that hides in places far smaller than a ventricle or a femur, far below anything a magnetic field could photograph. It does not live in the architecture of the brain or the lattice of the bone. It lives in the instructions the body reads to build and rebuild itself, moment by moment, cell by cell, the quiet inherited code that decides what every tissue is and how it behaves. The skeleton can be measured. The mind can be imaged, but the code that writes them both leaves no picture behind when it changes. And on the way to Mars, it changes too. To watch a change that casts no shadow, science needed something the body almost never offers. It needed a control. Not a chart of averages, not a population studied across decades, but a second copy of one specific person, the same genome written twice, with one copy lifted off the planet, and the other left exactly where it was. Nature provides this only in the rarest accident of biology: identical twins. Two people who began as a single cell that split, carrying the same inherited instructions down to the smallest detail. And in the second decade of the 21st century, NASA found itself holding precisely that instrument. Two men. One code, expressed in duplicate. Scott Kelly and Mark Kelly were born identical twins, and both of them became astronauts, which is its own quiet improbability. In March of 2019, the results of what NASA called the Twins Study appeared in the journal Science. The design was almost severe in its simplicity. Scott Kelly spent 340 days aboard the International Space Station. His brother Mark remained on the ground. For nearly a full year, one twin orbited the Earth while his genetic mirror ate ordinary food, breathed ordinary air, and slept under ordinary gravity. Whatever space does to the deep machinery of a human being would not have to be guessed at. It would appear as the growing difference between two men who, by every rule of biology, should have remained the same. To understand what they found, you first have to understand what they were not looking for. They were not searching for changes to the genes themselves, to the fixed sequence of chemical letters Scott inherited at the moment of conception. That sequence is remarkably stable. It is not the letters that shift in orbit, it is the reading of them. Every cell in your body carries the same complete library of genetic instructions. What makes a bone cell and a nerve cell is not which book it owns, but which pages it opens. This is gene expression, the constant silent decision about which instructions to switch on and which to leave closed. It is how a single fixed code produces a liver, a retina, a thought. And it is exquisitely sensitive to the environment the body finds itself in. When Scott Kelly returned to Earth, most of that machinery settled back toward normal, as expected. But not all of it. Roughly 7% of his gene expression had not returned to its pre-flight baseline. Not 7% in the first chaotic days of readjustment, when anyone might be forgiven for running strange. 7% still altered 6 full months after he had come home. Genes involved in immune function, in DNA repair, in the way cells handle the stress of being alive, remained switched into a configuration that the year in space had written, and the year on Earth had not erased. This distinction matters enormously. A body that has been bruised will heal and forget. A body that has had its instructions rewritten does not simply forget. It keeps reading the new version. For more than half a year, a measurable fraction of Scott Kelly was still, in the most literal cellular sense, running the program of a man in orbit while standing on solid ground. And then there was the part of the study that the world misunderstood almost completely. At the ends of every chromosome sit structures called telomeres. Think of them as the plastic caps on the ends of a shoelace, the small protective tips that keep the strands from fraying. Every time a cell divides, those caps grow a little shorter. Over a lifetime they wear down, and their shortening is one of the clocks the body uses to mark its own aging. Short telomeres are a signature of cells that are old, stressed, and close to giving out. By the logic of decades of research, telomeres are supposed to do one thing across a human life: get shorter. Scott Kelly's telomeres got longer. When that finding first surfaced, the story almost wrote itself. An astronaut goes to space and comes back biologically younger. It was an irresistible headline, and it spread exactly the way irresistible headlines do. The trouble is that it was wrong. Not partially wrong, not a matter of overstatement. Backwards. The lengthening was not a sign of rejuvenation, and what happened next made that unmistakable. The reason the misconception took hold is easy to trace. Telomeres are tied to aging in the public mind. Longer is intuitively better than shorter, and a story about a man returning younger from the stars is far more comfortable than the truth. But length alone is not health. A telomere that lengthens under extreme stress is not a body growing young. It is a body doing something abnormal under duress, and abnormal is rarely a gift. The proof came in the landing. Within 48 hours of Scott Kelly's return to Earth, his telomeres did not drift gently back toward where they had started. They collapsed. In 2 days, the lengthened caps shortened dramatically, and they did not stop at his pre-flight baseline. They fell below it. He did not come home the same age he left. By this particular measure, he came home older than the man who had launched, and older than the twin who had never left the ground. The space-grown length was not a reserve of youth. It was a spike that the body paid for, with interest, the moment it returned to gravity. This is the shape the entire mission imposes on a human being. Not a clean injury that heals on a known schedule, but a rewriting whose consequences arrive on their own timetable, sometimes years later, sometimes in the first 48 hours, almost never when you expect them. The bone gives you a number, the brain gives you an image, the genome gives you nothing to hold. It simply keeps running the altered code and waits. Consider what this means for a journey to Mars. Scott Kelly spent 340 days in low Earth orbit, and 340 days were enough to leave a measurable part of his biology rewritten half a year after he had landed. A conjunction-class mission to Mars does not last 340 days. It lasts more than 900, nearly 3 times as long, with much of it spent in deep space far from the planet that made us, the body reading and rereading an altered version of its own instructions the entire way out, the entire stay, and the entire way home. The twin study did not measure that journey. It only showed us the first faint edge of it, and the edge alone was enough to unsettle the people who ran the numbers. And the rewriting does not stop at telomeres and gene expression. It reaches into the part of the body whose entire job is to stand guard. And it does something stranger than weakening it. It redirects it. Inside every one of us lives a quiet population of viruses we have already met and supposedly defeated. The chickenpox of childhood does not leave. The cold sore that vanished does not truly vanish. These viruses retreat into nerve tissue and wait, held in permanent check by an immune system that never stops watching, never lowers the patrol. For most people, for most of their lives, that surveillance holds without a single conscious thought. The watchman does not sleep. Spaceflight makes the watchman look away, not by exhausting the immune system in the simple sense of wearing it down, but by actively pulling its attention elsewhere. The stress of the environment elevates cortisol and adrenaline, the same hormones that flood the body in moments of danger, and sustained at high levels they suppress the specific T-cell immunity that keeps those dormant viruses pinned down. The defense is not destroyed, it is reassigned. And in the gap that opens behind it, things that had been waiting a very long time begin, quietly, to wake. And waking is not a metaphor here. It is a measured, repeatable fact, documented again and again in the blood and the saliva of people who have flown. The immune system that looked away did not look away briefly. In the conditions of long spaceflight, it can stay turned for the entire duration of a mission, and for weeks after the wheels touch down. What it stops guarding, across those long unguarded stretches, is a list longer and more familiar than most astronauts would ever have guessed. In 2019, a team of researchers publishing in the journal Frontiers in Microbiology gave that quiet waking a precise shape. They examined the blood and the saliva of astronauts before flight, during flight, and after their return, hunting for the genetic fingerprints of viruses from the herpes family. These are not exotic organisms. They are the ordinary companions of ordinary human lives, arriving quietly in childhood and then falling silent, folding themselves into nerve cells and immune cells and waiting, sometimes for the rest of a person's life. The study found them stirring, not in a rare and unlucky few, but across the clear majority of the people who had flown. Among the space shuttle astronauts, whose missions lasted only 10 to 16 days, 47 of 89 showed reactivation. That is 53%. More than half, from journeys measured in mere days. Among the astronauts who lived aboard the International Space Station for 180 days or more, the figure rose to 14 of 23. 61%. The pattern was not subtle. The longer the body remained in orbit, the more of these sleeping viruses opened their eyes. On the long station missions, the shedding climbed to levels that would unsettle any physician on the ground. The Epstein-Barr virus appeared in the samples of 96% of crew. The varicella-zoster virus, 65%. The cytomegalovirus, 61%. None of these were infections caught from a sick crewmate or carried aboard on a cargo flight. Every single one was already living inside the astronaut who carried it, dormant for years, often for decades, waiting for precisely these conditions. Not a new enemy arriving from outside, but an old one, set loose by the journey itself. This is the place where a comfortable picture of illness has to be carefully taken apart. When we imagine a person falling sick in space, we tend to imagine contamination, a stray microbe smuggled in along a waterline, a cough passed across a cramped cabin, an infection that came, somehow, from somewhere outside the body. That picture is not merely a little inaccurate, it is aimed in entirely the wrong direction. The most reliable biological threat aboard a long mission is not anything that comes in from the world. It is what was already there, silent and patient, inside the crew before they ever left the launch pad. The journey does not import the danger. It quietly unlocks a door that the immune system had spent an entire lifetime holding shut, and that door does not swing closed the instant the spacecraft touches down. The varicella-zoster virus and the cytomegalovirus continued shedding in some astronauts for up to 30 days after they had returned to Earth. A full month back beneath the planet's protection, breathing its thick air, sleeping again in its gravity. And still, the awakened viruses kept surfacing in the blood and the saliva. For most of those astronauts, the reactivation remained silent, visible only to a laboratory. But not for all of them. 6 developed symptomatic herpes illness, the dormant infection no longer a faint signal on a test, but a visible condition in the body of a person who had left Earth perfectly healthy. Now consider what this means stretched across a journey to Mars. The reactivations measured so far come from missions of a few weeks, or of 6 months at the very outer edge of human experience. A conjunction-class crossing holds the body in these same conditions for more than 900 days. The cortisol elevated, the T-cell surveillance pulled steadily away, the unlocked door held open not for a fortnight but for years on end. There is no reason to expect the viruses would wait politely for a more convenient time. There is every reason to expect that the longer the watchman looks away, the more of the sleeping things will rise, and the longer they will keep rising even after the watchman finally turns back to his post. Picture what that watchman actually is. The immune system is not a wall, it is a standing garrison, a population of cells that must constantly patrol the body, recognizing what belongs and what does not, keeping the dormant viruses pinned in place by sheer vigilant attention. Vigilance is expensive. It demands resources, attention, and a body that feels safe enough to spend them. Strip that sense of safety away, flood the system with the chemistry of permanent alarm, and the garrison is quietly redeployed to threats that feel more urgent. The viruses do not break through a defense. The defense simply stops watching them, and what no one is watching is, eventually, free to move. There is a further cruelty folded into all of this. The very immune cells that ought to be hunting down these reactivated viruses are themselves diminished by the same flight. Studies have found that astronauts' immune cells become measurably less effective during spaceflight, and that this weakness can linger for as long as 60 days after they come home. So the door stands unlocked at the precise moment the guards are fewest and least capable. The timing could hardly be worse if it had been designed. The threat is not limited to the viruses the astronaut carried up with them. The microbes that live inside any spacecraft sharing the recycled air and the warm surfaces and the moisture of human breath, are changed by the same radiation that changes the crew. After exposure to the conditions of space, some of these microorganisms develop resistance to antibiotics, to ultraviolet light, to heat, and to drying out. The medicines a doctor would normally reach for grow less certain. So the full picture is this: a suppressed crew, a population of hardened and more resilient microbes, dormant viruses waking from within, and the nearest hospital tens of millions of miles behind them. There is no quick flight home. There is no resupply of a drug that suddenly stops working. There is only the body, the crew, and whatever they brought with them. Here is where the entire story of the Mars traveler turns on itself. Until now, the damage we have followed has mostly been a story of subtraction. Bone quietly removed, brain tissue displaced and slow to settle back, structure worn thin and reluctant to return. But the immune story is different in kind. Nothing here is being taken away at all. Something is being switched on. The body is not simply being depleted by the journey. It is being reprogrammed by it. Its priorities are rewritten. Its silent passengers are granted permission to wake. This is not the body losing a fight against the void. It is the body faithfully following a new set of instructions, and those instructions are being written by an environment that was never, in any sense, meant to hold a human being. That is the deeper meaning of a body that rewrites its own code. It is not only the genetic readout that refuses to switch fully back to who a person was before they left. It is the standing arrangement between a human being and the organisms they have carried, unspoken and unbroken, since childhood. On Earth, that arrangement holds for a lifetime. The viruses sleep, the body watches, and the peace endures so quietly that most people never learn it was being kept at all. The journey to Mars breaks that peace, not violently, not all at once, but steadily, the way a long absence loosens a grip that once felt permanent. And the unsettling part is how little the traveller would feel of it while it happened. There would be no fever announcing the change, no single moment of crisis to point to, only a slow, invisible rearrangement, measured in the laboratory long before it could ever be felt. A person could spend the entire crossing believing themselves unchanged, healthy, intact, carrying their own waking passengers the whole way, and not learning the full list of them until long after they had arrived somewhere no human body was ever shaped to go. There is, however, one change the traveller would not need a laboratory to confirm. This one announces itself in the only place a person can never look away from. It happens inside the eye. Somewhere in the first weeks of the journey, often as early as the third week, the back of the human eye begins to change its shape. The eyeball is very nearly a perfect sphere, a small globe of fluid and tissue that we trust without ever once thinking about it. And in the absence of Earth's steady downward pull, that sphere slowly flattens at the rear. The doctors who first studied long-duration crews aboard the International Space Station gave this collection of changes a careful clinical name. They call it spaceflight-associated neuro-ocular syndrome. The astronauts who reported it described a strange and unwelcome discovery. Vision that had been sharp for a lifetime was going soft. The flattening of the globe is only where it begins. The optic disc, the place where the nerve leaves the eye and carries sight to the brain, begins to swell. The retinal nerve fiber layer thickens with fluid. Fine folds appear in the choroid and the retina, the way a smooth sheet wrinkles when it is pushed from beneath. And the eye's focus drifts, shifting toward farsightedness by 3/4 of a diopter or more, enough that an astronaut who could read fine print on the day of launch may need correction to read it now. This is not the ordinary tiredness of strained eyes. It is a physical remodeling of the organ itself. Consider what this means. The eye does not lose its sharpness because the traveller is exhausted, or because the lighting is poor. It loses its sharpness because its very architecture has been bent. Not bent by injury, not bent by a blow, but bent by the quiet, constant fact that fluids in the body no longer know which way is down. On Earth, gravity pulls blood and cerebrospinal fluid gently toward the feet, and the body has spent millions of years assuming that pull will always be there. Remove it, and the fluids rise. They gather in the skull. They press outward against the back of the eye from the inside, and over weeks and months they reshape it. Here is the part that should make the breath catch. Many of these changes do not reverse when the journey ends. The choroidal folds can remain. The flattening of the globe can persist. The shift in refraction can stay with the astronaut long after their feet have touched Earth again. The swelling fades. The structure does not always follow. A person can come home, walk into a clinic, sit before the same charts they once read with ease, and find that their eyes have been permanently resculpted by a place that had no gravity to shape them. And here is what makes the eye different from almost every other change in this story. No astronaut has yet gone blind from it. No mission has been lost to it. No single case of permanent significant vision loss has ever been recorded. That sounds at first like reassurance. It is not reassurance. It is the most unsettling fact about the syndrome, because every flight on which it has been measured was a flight counted in months. The damage appears to accumulate. It builds with time spent in the absence of gravity, and so far no one has found the ceiling, the point where it stops getting worse. Not because the ceiling has been located and judged safe, but because no human being has ever stayed up there long enough to find it. To appreciate how this truly matters, consider the arithmetic of distance. Every astronaut who has shown these eye changes was home within roughly half a year, a season, a stretch of time the body could survive and partly mend. A journey to Mars is not measured in seasons. It is measured in years. More than 900 days for a conjunction-class mission. A year and more before the surface is even reached. And the body never once steps outside the fluid shift that bends the eye. The astronauts who have flown so far have been like swimmers testing the shallow end of a pool whose deep end has never been charted. We know the water reshapes the eye in the shallows. We have never sent anyone far enough out to learn what it does when there is no shore in sight for years at a time. And the eye, as quietly as it suffers, is not even the organ that betrays the traveller most reliably. There is another change, older and more familiar than any of these, that turns against the human body the moment it leaves the ground. It is sleep, the thing every living person on Earth does without instruction. The thing the body is supposed to be able to do anywhere, in any condition, as a last resort against exhaustion. In space, even that quiet certainty falls apart. The numbers are stark, and they come from years of careful record-keeping aboard the International Space Station. Across 2,951 recorded nights of astronaut sleep, the crews slept fewer than 6 hours on 1,294 of them. That is 43.8% of all nights, nearly half, spent below the threshold that sleep scientists consider the bare minimum for a functioning adult. These are not careless people. These are among the most disciplined, most medically monitored human beings who have ever lived, following schedules built by experts whose entire purpose is to keep them rested. And still, on close to half their nights in orbit, real rest did not come. Their bodies fought back against the silence in the most human way available. They reached for medication. Sleep aid use among astronauts runs roughly 6 times higher than it does among the general public on Earth. Where about 12% of people on the ground turn to something to help them sleep, roughly 75% of astronauts do. 3 out of every 4, not because they are weak, and not because they are anxious by nature, but because a body removed from gravity loses some quiet signal it is always depended on to fall and stay asleep, and chemistry becomes the only way to recover what the planet once gave for free. The pattern grows worse on the nights when rest matters most. Before a spacewalk, before the most dangerous and demanding hours an astronaut will ever face outside the protective walls of the station, 51.3% of crew slept fewer than 6 hours. More than half went into the hardest work of their lives under-rested. And on those same critical nights, only 1.3% managed a full 8 hours. Barely one astronaut in 100 walked into a spacewalk having slept the way a person on Earth is told they must sleep before merely driving a car. And even the sleep they did manage was not the sleep their bodies needed. The deepest, most restorative phase, the dreaming stage scientists call REM, fell sharply in orbit. Compared to their own measurements before launch, astronauts lost between 26.6 and 50% of their REM sleep. In the worst cases, half of the most essential layer of rest simply vanished. The body lay still in its tether, eyes closed, hours passing. But the dreaming brain, the part that consolidates memory and repairs the mind, was being quietly starved. The traveller could spend a full night appearing to sleep and wake, having received only a fraction of what sleep is for. Now carry that broken sleep to Mars, and the problem does not stay the same. It deepens. Because Mars keeps a different kind of time than Earth does, and the human body was never built to follow it. A single day on Mars, one full turn of that red world from one sunrise to the next, lasts 24 hours, 39 minutes, and 35 seconds. It is longer than an Earth day by roughly 40 minutes. That sounds like almost nothing. 40 minutes is the length of a slow lunch, a short walk, a single episode of something forgettable. On the human clock, it is not nothing at all. The body keeps time with a master rhythm wound tight to the 24-hour spin of the planet that made us. A rhythm built into nearly every cell across millions of years of sunrises. Stretch each day by 40 minutes, and at first the gap seems trivial. But the days do not come one at a time. They stack. 40 minutes becomes a few hours within a week, becomes a full inversion within a fortnight, the internal clock and the external day drifting apart until the traveller is wide awake when the Martian sky is dark and heavy with sleep when it is bright. Not because the traveller is undisciplined, and not because the new schedule is poorly designed, but because the body is still, stubbornly, keeping the time of a world more than 30 million miles behind it. And it is not a problem that discipline can solve. The will is strong, but the clock inside the body is older and far more patient. Researchers studied this directly, placing people on the Martian schedule and watching what their sleep actually did when nobody was allowed to cheat. When the internal clock stayed aligned with the Martian soul, when the synchronization held, the body managed an average of 5.98 hours of sleep each night. Not 8, not 7, barely 6. And that was the success story. That was the version where everything worked. The mission control workers who tracked the Phoenix Mars lander across the surface of another planet lived on Martian time for the length of the operation, and even with rigorous scheduling and full institutional support, 6 hours was the ceiling, not the floor. Then there was the other outcome. When the internal clock slipped out of step with the Martian day, when alignment failed and the body insisted on keeping Earth time inside a Martian house, average sleep collapsed to 4.91 hours per night, give or take a little over an hour in either direction. That is the difference between a tired person and a broken one. 4 hours and 55 minutes of sleep is not a rough night. It is a clinical state. Sustain it for a week and judgment phrase. Sustain it for a month and the body begins to fail in ways that have nothing to do with effort. And the studies were clear about what accompanied that collapse. Fatigue rose. Sleepiness rose. The capacity to think clearly and react quickly, the very faculties an isolated crew would need most, eroded exactly when the margin for error was thinnest. The hopeful number, the one that sounds like a solution, is that 87% of tested participants could eventually adapt their circadian rhythm to the Martian soul. Read quickly, that is reassuring. Read slowly, it is a warning, because 87% adapting means 13% did not. 13% of people simply could not retrain the master clock to a 40-minute longer day, no matter how the schedule was arranged. On a crew of 6, the mathematics are brutal in their plainness. 13% of 6 is most of one whole person. A crew sent to Mars could carry, statistically, a member whose body would never synchronize to the planet they were standing on. Not for lack of trying, not for lack of training, simply because that particular nervous system was built to a tolerance the Martian day exceeds. And this is the optimistic frame, the version where sleep is merely difficult rather than already broken. The data from orbit suggests the breaking begins long before Mars enters the picture. On the International Space Station, where astronauts are the most monitored, most supported, most carefully scheduled human beings ever to leave the ground, sleep was studied across thousands of nights. The result was not encouraging. Crews slept fewer than 6 hours on 43.8% of recorded nights. That is 1,294 nights of insufficient sleep out of 2,951 nights measured. Nearly half. Not occasionally, not during emergencies, but as the ordinary texture of life in space. The astronauts were not failing. The environment was simply incompatible with the kind of rest a human body requires, and so they reached for help. Sleep medication use among astronauts runs approximately 6 times higher than among the general population on Earth. Roughly 75% of astronauts used sleep aids during their missions, compared to roughly 12% of people on the ground. Consider what that figure quietly admits. 3 out of every 4 people in the most selective, most physically resilient profession on the planet could not fall asleep in space without chemical assistance. Not because they were weak. These are among the most disciplined humans alive, but because the body, deprived of the gravity and the light and the steady 24-hour turning it was built around, forgets how to let go. The worst nights came when the work mattered most. Before a spacewalk, before the single most dangerous and demanding task an astronaut performs, the body should be rested, the mind sharp, the reflexes whole. Instead, on the nights before those spacewalks, 51.3% of crew members slept fewer than 6 hours, and only 1.3% managed a full 8. Think about that ratio. For every 100 astronauts preparing to step into the vacuum, fewer than 2 arrived at the airlock having slept the amount a human actually needs. The rest went out tired, into an environment that punishes the smallest mistake with the largest possible consequence. Not because they were careless, but because rest in that place had become a luxury the body could no longer reliably afford. There is a deeper cut still, and it lives below the surface of the numbers, in the architecture of sleep itself. Sleep is not a single state, it is a layered descent, and the deepest, strangest layer is REM, the phase where the eyes move beneath closed lids, where dreaming happens, where the brain files the day's experiences into memory and quietly repairs the emotional damage of being alive. REM is not optional, it is where the mind tends itself. And in space, REM sleep decreased by somewhere between 26.6% and 50% compared to the astronauts' own baselines on Earth. In the worst cases, half. Half of the most restorative sleep a human gets, the sleep that consolidates memory and stabilizes mood and processes fear, simply gone. Not delayed, not rescheduled to a quieter night, erased from the ledger entirely. Now hold all of this against the clock of an actual Mars mission, and let the deep time of the thing settle over you. This is not a fortnight in orbit. This is not a single difficult expedition with a return date on the calendar. A conjunction-class mission to Mars runs more than 900 days, more than 2.5 years, nearly 1,000 consecutive nights, each one fought on a battlefield where the body is already losing. 900 days of sleep that breaks against a Martian day 40 minutes too long. 900 nights of REM stolen in fractions until the missing hours stack into months. 900 mornings of a brain that was never allowed to finish the work the night is for. Not one bad week, not one rough season. 1,000 of them in a row, in a place where no replacement crew can arrive, and no early return is possible once the launch window has closed behind you. And the cruelty is in the compounding, because none of these failures happen in isolation. The body that cannot sleep, is the same body absorbing 1.8 millisieverts of cosmic radiation a day. The brain whose ventricles have swollen and whose white matter is aging at twice the normal rate is the same brain being asked to function on 4 hours and 55 minutes of sleep. The immune system, already weakened by microgravity, is weakened further by every night the cortisol stays high because the rest never came. These are not separate problems standing in a line waiting their turn. They are a single problem wearing many faces, each one feeding the others, each deficit deepening the next. Not a list of risks, a web of them, and the traveler is sitting at the center. What emerges when you assemble the full picture of the body on a Mars mission is something that sounds less like medicine and more like erosion, a slow, total, systemic wearing away that touches the bones and the eyes and the blood and the brain and the sleep, all at once, for years, with no respite and no exit. The remarkable thing is that the human body endures it at all. It does not thrive. It does not adapt in any complete sense. It simply holds the way a coastline holds against the tide, losing a little more of itself with every cycle, never quite collapsing, never quite whole. But there is one more layer beneath even this, and it is the layer the numbers struggle to reach. The bones can be measured, the radiation can be counted, the sleep can be charted to the minute, and the eyes can be photographed in their slow deformation. The mind cannot be photographed, and it is the mind, more than any organ, that pays the strangest and most lasting toll of all, because the mind on the way to Mars is not merely tired or stressed or afraid. It is something humanity has never produced before. It is a consciousness severed from the world that made it, cut off by a gulf so wide that even light itself arrives late. Consider what it means for light to arrive late. On Earth, the people we love are never more than a heartbeat away. We speak, and we are heard. We call out in the dark, and an answer comes before the fear can fully settle. The gap between a word leaving the mouth and reaching another person is so small that no human being has ever had to think about it. It is the invisible flaw beneath every conversation our species has ever had. On the way to Mars, that flaw gives way. The distance is what undoes it. As a spacecraft falls outward toward the red planet, the gulf between it and Earth swells from 35 million miles at the closest approach to as much as 250 million miles at the farthest. Light is fast. It is the fastest thing there is, and yet across that widening emptiness, even light begins to crawl. A single message, traveling at the absolute speed limit of the universe, takes anywhere from 5 minutes to 35 minutes to cross from one world to the other. Then the reply must make the same long journey back. This is not a delay you can speak over. It is not the small lag of a distant phone call, where two voices stumble politely across each other and then recover. It is a silence with a shape. A question asked of Earth, and the answer that follows can be separated by as much as 50 minutes of total round-trip time, with the average closer to 25. Ask for help. Then wait. Ask whether the reading climbing on the panel is dangerous. Then wait. NASA has studied this threshold carefully, and the conclusion is stark. Beyond a delay of roughly 5 minutes, real-time guidance from the ground becomes impossible, and the crew must begin to act on their own authority. Consider what this means in an emergency. A fire, a slow leak bleeding pressure into space, a medical crisis unfolding inside a metal can drifting between two planets. On Earth, mission control has always been the second brain of every crewed flight, a room full of calm experts watching every gauge, ready to talk an astronaut through the worst minutes of a life in real time. That room does not vanish on the way to Mars, but its voice arrives too late to matter. By the time the warning reaches the ground and the answer travels back, the moment that needed it has already passed, one way or the other. The crew is not merely far from home. They are, for the first time in the history of human exploration, genuinely and structurally alone. We know something about what that solitude does to people, because we have rehearsed it, not on Mars, but in a windowless facility on the outskirts of Moscow. On the 3rd of June, 2010, 6 men sealed themselves inside a cluster of pressurized modules at the Institute of Biomedical Problems and did not step outside again for 520 consecutive days. The crew was 3 Russian, 2 European, and 1 Chinese, with an average age of 32. The whole habitat enclosed roughly 550 cubic meters, smaller than many family homes, and within it the men ate, slept, exercised, ran their experiments, and pretended to fly to Mars, to land upon it, and to return. It remains the most extensive Mars mission simulation ever conducted. They never left the building. They simulated the distance, the delay, and the silence with painstaking care, and then they let the months do the rest. What the experiment revealed was quietly unsettling. The crew did not turn on one another. That is the part most people expect, and it is the part that did not happen. The 6 men did not fracture into warring camps inside their narrow world. Conflict among the crew was rare, recorded only 8 times across the entire mission. Instead, the friction flowed in a different direction. Conflicts between the crew and mission control occurred 41 times, more than 5 times as often as conflict among the men themselves. The people inside the can did not come to resent each other. They came to resent the distant voice of Earth, the voice that issued instructions from across a gulf it could not feel. This is not the failure the early planners feared. They worried about cabin fever, about crewmates at each other's throats in a shrinking space. But the deeper rupture was not between the people who shared the silence. It was between those people and the world that had sent them. A world that kept speaking, kept directing, kept asking, while growing day by day more abstract and more remote. The bond that frayed first was not the bond between the crew. It was the cord that tied the crew to home. The body too began to withdraw. 4 of the 6 crew members grew steadily more sedentary as the mission wore on, moving less, exercising with less conviction, sinking into the long flat sameness of days that no longer had a horizon. And the rhythm of sleep, that fragile thing we have already watched come apart in orbit, came apart here as well, on the ground, with gravity fully intact. 2 of the 6 men drifted out of step with the clock entirely. One slipped into a free-running cycle of roughly 25 hours, his body quietly insisting on a day that did not match the one printed on the wall. The other broke his sleep into pieces and scattered them across the hours. They were not sick. They were not weak. They were simply human beings whose inner world had begun to detach from the outer one. Consider what this would feel like from the inside, not as a data point, but as a life. You wake on the 90th day, or the 300th, in the same small room you have woken in every morning for longer than you can easily hold in your head. The same few faces, the same recycled air with its faint mechanical smell, the same view of nothing through windows that show only more of the ship. You think of someone on Earth, and you write to them, and you understand as you send it that the version of them who reads your words lives 20 minutes in your future, and that their reply belongs to a moment you have not yet reached. Every exchange is a letter dropped into a deep well. You hear the splash long after the stone has gone. This is the true texture of the isolation, and it is unlike almost anything in ordinary human experience. We have always had distance. Explorers have sailed for years beyond the reach of any rescue, but even the loneliest sailor on the emptiest ocean lived beneath the same sky as the people he had left. He breathed air they could have breathed, and he could, in principle, turn the ship around. The crew bound for Mars can do none of these things. They cannot turn around. Once the trajectory is committed, the planets themselves must wheel into alignment before a return is even possible, and that alignment can be a year or more away. There is no early exit from a journey to Mars. There is only forward, and then the long, patient wait for the door to open again. To understand how the mind actually moves through such a stretch of time, researchers turn to the slope of a volcano. On the flanks of Mauna Loa in Hawaii, a small domed habitat became the stage for a series of long isolation studies known as high seas, in which 6 volunteers at a time lived sealed away for missions lasting 4 months, 8 months, and 12 months. What the researchers watched unfold was not a single steady decline, but a sequence, a kind of inner weather that the isolated mind passes through in phases, each one shading into the next. The first phase is almost bright. In the opening days, the body floods with the chemistry of challenge, a surge of cortisol and adrenaline that researchers call eustress, the good stress, the lift of a hard thing freely chosen. The crew is alert. The mission feels real and worthy of them. The discomforts are still novel enough to hold a certain interest. The mind leans forward into the work, hungry, engaged, certain it can carry the weight. But this phase does not last, and the chemistry that comes to replace it runs in the opposite direction. As the weeks compound into months, the brain's reserves of dopamine and serotonin begin to run low, drained by the unrelenting sameness, worn down by the absence of the small rewards that ordinary life scatters so freely across every single day. There is no new face. There is no change of weather worth the name. There is no walk that leads anywhere the eye has not already memorized 100 times. And the mind that began the mission reaching eagerly outward begins, slowly and almost without notice, to turn itself down. This is the third phase, and it does not announce itself with a single dramatic moment. The researchers behind the high seas studies, who sealed 6 volunteers at a time inside a small dome on the slopes of Mauna Loa in Hawaii for missions of 4, 8, and 12 months, watched it arrive as a quiet erosion. The individual begins to fray first. Then the bonds between individuals begin to fray with him. What had been a team becomes a set of people who happen to share an air supply. Small irritations that a single good night of sleep would have dissolved instead accumulate, hardening into grievances that no one says aloud. The shared rhythm that once held the crew together loosens thread by thread, until each person is keeping a slightly different time than the others. This is the disruption of individual and team dynamics, and it is not a failure of character. It is a predictable stage in a known sequence, as reliable as the chemistry that produced it. And then comes the fourth phase, the one the researchers named asynchronous coping. Each crew member, drained and worn, begins to manage the unbearable sameness in their own private way. One person shifts their sleeping hours later and later, another splits their rest into fragments scattered across the day. The waking hours of one no longer overlap cleanly with the waking hours of another. Team cohesion, already thinning, frays further as the crew quite literally stops sharing the same hours of consciousness. They are still in the same small space. They are simply no longer living in the same day, not separated by walls, but separated by time itself, each retreating into a schedule of their own making. Here is the part that resists easy storytelling. The high seas researchers found substantial differences between individuals, and some crew members showed no measurable behavioral disturbance at all across 17 months of isolation. The 4-phase descent is not a sentence handed down equally to everyone who leaves the Earth. Some minds simply hold. Whether this is temperament or training or some quality we have not yet learned to name, nobody can say with confidence. The honest answer is that we do not yet know who breaks and who endures, and that uncertainty is itself one of the heaviest risks any Mars crew would carry into the dark. To see how this plays out across a journey of true Martian length, consider the most extensive Mars mission simulation ever conducted. On the 3rd of June, in the year 2010, 6 men sealed themselves inside a windowless complex at the Institute of Biomedical Problems in Moscow. 3 were Russian, 2 were European, 1 was Chinese, and their average age was 32. The chamber held 550 cubic meters of pressurized volume, a space smaller than many modest homes, and they would not step outside it for 520 consecutive days. They emerged on the 4th of November in the year 2011, having simulated the full arc of a mission to Mars and back without ever leaving the city of Moscow. What the Mars 500 crew revealed was not loud breakdown, but slow withdrawal. 4 of the 6 men grew increasingly sedentary as the months wore on, moving less, doing less, the body following the mind downward into stillness. 2 of the 6 developed non-standard sleep patterns that mirror the high seas findings with unsettling precision. One drifted into a free-running cycle of roughly 25 hours, his internal clock untethering from the calendar entirely, each day beginning an hour later than the last, until his nights and the crew's days slowly traded places. Another fractured his rest into a pattern of split sleep, taking it in pieces rather than in one whole. Within a single sealed chamber, the crew's days were quietly coming apart. But the most revealing number from Mars 500 was not about sleep at all. It was about anger, and about where the anger went. Conflicts between the crew and their distant mission control occurred 5 times more often than conflicts among the crew members themselves. 41 disputes with the ground against only 8 within the cabin. Consider what this means. The 6 men did not turn on each other. They turned together against the voices outside. The people in the room became the only allies. The people on the other end of the radio became the problem. It is a strange and almost tender finding, this instinct to close ranks against the outside world, and it carries a warning that grows sharper the farther from Earth a real crew would travel. Because on a true Mars mission, the outside world cannot answer quickly. This is the part that no simulation in Moscow or on Mauna Loa can fully reproduce, because the chamber crews always knew that help, in truth, was only a door away. A real crew would know the opposite. The one-way communication delay between Mars and Earth ranges from 5 minutes to 35 minutes, depending on where the 2 planets sit in their orbits. Because Mars wanders between 35 million and 250 million miles from us as both worlds circle the Sun, the average round-trip delay runs to roughly 25 minutes. You speak a sentence, and you wait. The reply, when it comes, is already old. Think about what that delay does to a conversation. Not a pause you can talk over. Not the awkward lag of a poor connection. A silence long enough to make a cup of coffee and drink it before the answer to your question arrives. NASA acknowledges that beyond a delay of just 5 minutes, crews must begin to operate with increasing autonomy, because the back and forth that mission control has relied upon since the first days of human spaceflight simply stops working. And during a true emergency, the kind measured in seconds, real-time support from the ground is not merely difficult, it is impossible. A fire, a sudden illness, a failure of the systems keeping the crew alive. In those moments, the nearest help capable of useful instruction is a quarter of an hour away at the speed of light, and the crew is, in the most absolute sense the word allows, alone. So the Mars 500 finding turns from curious to chilling. A crew that closes ranks against mission control is a crew learning, in advance, what a real Mars crew would be forced to learn for real. The ground is no longer the parent. The ground is a delayed and distant voice, helpful for planning and useless for rescue. The team in the room is all there is. Their cohesion is not a comfort, it is the entire safety system. And cohesion, as the 4-phase model shows, is precisely the thing that the long dark erodes first. This is the final layer of the changes a Mars mission would write into a human being, and it is the only one that lives entirely above the neck, in the place where a person keeps the sense of who they are. The radiation rewrote the cell, the microgravity rewrote the bone and the eye and the brain. The isolation rewrites something harder to measure and harder to repair, the bond between a mind and the world it came from, and the bond between that mind and the few others sealed into the dark alongside it. The body, given years, may claw back most of what it lost. Whether the mind returns the same is a question no measurement has yet answered, because the deepest changes leave no scan, no marrow sample, no shift in gene expression to point to. They leave only a person who has spent the better part of 3 years severed from the Earth, and who must now learn, somehow, to belong to it again. There is a temptation, standing at the end of a list like this one, to read it as a verdict, to treat the rewritten cells and the thinning bone and the swelling brain and the waking viruses as a single sentence handed down against the whole idea of going. That reading is understandable. It is also almost certainly too simple. The facts do not say that a human being cannot reach Mars. They say something quieter and stranger. They say that a human being cannot reach Mars and return unchanged, and that some fraction of the change will not undo itself, no matter how many years of Earth and gravity and ordinary mornings are poured over it afterward. The body keeps a ledger. Most of the entries can be paid back. A few of them cannot. So we arrive at a question that has no clean answer, and it is worth saying plainly that it has no clean answer. Perhaps the journey is worth it. Perhaps standing as the first human being on the surface of another world, watching a dawn no member of our species has ever watched, would justify every gene left switched into a new pattern, and every % of femoral bone that never finds its way home. Perhaps the meaning of such a thing is large enough to carry the cost without strain, or perhaps the human spirit needs the world it came from more than it needs the worlds it has not yet touched. Perhaps belonging to the earth is not a cage to be escaped, but the very thing that makes a person able to leave it and still remain a person. These are not questions that physics can settle. The instruments have done their part. The Curiosity rover measured the radiation falling on the road to Mars and found 1.8 millisieverts every single day of the crossing. The studies counted the bone and found that on the longest missions every astronaut crosses into osteopenia, and that more than half do not fully rebuild what they lost even a year after their feet touch the ground. The scans found the brain rearranged, its fluid cavities swollen by as much as 25%, its white matter aging at twice the ordinary rate. The genetic work found 7% of one man's gene expression still altered 6 months after he came down. The numbers are not in dispute. What the numbers cannot tell you is whether a transformed human being is a diminished one or simply a different one. And that is not a question for a laboratory. It is a question for the person who chooses to go. This is where the science quietly hands the matter back to us. Every measurement in this entire account describes what would happen to a body, not what it would mean to a life. A telomere collapsing below its baseline within 48 hours of landing is a fact. Whether that fact should frighten a would-be Mars traveller, or whether it is simply the toll at the gate, the price the universe charges for passage across 100 million miles of nothing is a judgment no microscope has ever made. The instruments can tell us the cost in cells and in years. They cannot tell us what the cost is worth. That valuation lives somewhere the radiation cannot reach, in the part of a person that decides against every reasonable warning that some horizons are worth being remade by. And here is the thing that the studies, taken together, almost seem designed to teach. There is no single answer, because there is no single human being. Mars 500 sealed 6 men into a chamber for 520 days, and they did not respond as one organism. 4 of the 6 drifted into a deepening stillness, moving less and less as the months wore on. 2 slipped their sleep loose from the clock entirely, one drifting onto a 25-hour rhythm, one splitting his rest into pieces. The same walls, the same dark, the same severing from the earth, and 6 different ways of bending under it. The isolation analogues on the slopes of Mauna Loa found the same truth written larger. Some volunteers came apart by degrees across the long months. Others moved through more than a year of confinement, with no measurable disturbance at all. The dark does not press equally on everyone. It finds the particular shape of each mind and tests it there. So the choice cannot be made for the species. It can only be made by individuals, one at a time, each weighing a private ledger that no one else can read. Different people will reach different verdicts, and both the yes and the no will be defensible. One person will look at the doubled cancer risk, at the bone that may take 3 years to rebuild and may never rebuild its inner scaffolding at all, and will recognize in that list a reason to stay. Another will look at exactly the same list and see only the entry fee for the most extraordinary thing a human being has ever attempted. Neither of them is wrong. The facts are identical. The meaning each person assigns to those facts is not something the facts can supply. It is something each person brings. This is the strange gift hidden inside all of this measured dread. The studies do not close the door. They describe, with great precision, exactly how heavy the door is, and then they leave the choice of whether to open it entirely to you. The radiation is real. The bone loss is real. The viruses stirring awake in the blood are real. The slow erosion of the mind across 1,000 days of silence is real. None of it is exaggerated for the sake of a story, and none of it forbids the journey. It only sets a price, and prices are paid by those who decide the thing on the far side is worth them. Consider what that actually asks of a person. To go to Mars under these conditions is not to gamble with the body in the way a soldier or a deep-sea diver gambles, accepting a risk that ends when the danger ends. It is to accept a permanent rewriting. The traveller who returns will carry a skeleton that is measurably less than the one that left, a brain whose fluid spaces may not regain their full elasticity for 3 years, if a second mission is ever attempted before then, beginning the swelling all over again. A genome that has filed away some record of the journey it may never fully erase. The person who comes back is, in a literal and measurable sense, not the person who departed. To choose Mars is to choose that exchange with open eyes. It is to say that the version of yourself who has stood on another planet is worth more than the version who never left, even though the second version is the only one with an intact thigh bone and an unswollen brain, and a quiet immune system that still remembers to keep its old viruses asleep. Most of us will never face that decision directly. The crews will be small, the missions rare, the volunteers few. Yet the question they answer for themselves belongs, in a smaller key, to everyone who has ever stood at the edge of something that would change them and could not be undone. The new country, the vow, the work that consumes a life. We rarely calculate these things in millisieverts or in percentages of lost bone. We feel them instead as a weight in the chest, a sense that crossing this particular line will make us into someone we cannot yet meet. The Mars traveller simply has the rare privilege and the rare burden of seeing the exact cost printed out in advance, measured to the decimal, before the choice is made. And once you see it that way, the distances themselves begin to feel less like obstacles and more like the simple terms of the offer. Mars is never closer than about 35 million miles and can swing as far as 250 million miles from the Earth. And at that gulf-even light, the fastest thing the universe permits needs somewhere between 5 and 35 minutes to make the one-way crossing. A cry for help sent from the Martian surface reaches home, on average, only after the round trip of roughly 25 minutes has elapsed, by which point whatever prompted the cry has long since resolved itself one way or the other. NASA states the consequence flatly. Past a 5-minute delay, the crew is on its own. Real-time rescue from mission control is not difficult across that distance. It is impossible. The traveller is not merely far from the Earth. The traveller is, in every moment that matters, beyond its reach. That is the true scale of what is being chosen, and it dwarfs the bone and the brain and the blood, because all of those are only the inward expression of this single outward fact. To go to Mars is to place yourself somewhere no hand can reach you, for the better part of 3 years, while the radiation does its slow work, and the silence does its slower work, and the Earth that made you shrinks to a pale point of light that answers, when it answers at all, a half-hour late. The body changes because the situation is unprecedented. The mind changes because no human being has ever been that alone for that long with that little chance of return. And the question, the only question, is whether a creature shaped entirely by the Earth, by its gravity and its days and its nearness and its noise, can carry all of that out into the dark and bring something recognizable back. Perhaps that is precisely what the first travellers will accomplish. Perhaps the changes the journey carves into them will turn out to be a kind of inheritance rather than a wound. The thin skeleton, the widened ventricles, the telomeres that grew long in orbit and then collapsed below where they began within 48 hours of landing, the 7% of gene expression that never fully returned to baseline. Perhaps all of it would be the toll the universe extracts for passage, and the passage would be worth the toll. Or perhaps the human animal needs the Earth more than it needs the stars. Perhaps a creature shaped by gravity and nearness, and the sound of other voices answering without delay, simply cannot remain itself once those things are taken away. Perhaps to sever a person from the world that built them is to lose the very thing the voyage was meant to carry. These questions have no universal answers. Different people will weigh them differently, and they will be right to. Some will look at the radiation and the bone loss and the silence and decide that no destination justifies them. Others will look at the same evidence and decide that the destination justifies anything at all. There is no equation that resolves this. There is only the choosing, and the choosing belongs to whoever stands at the threshold, not to anyone who explains the threshold afterward. Consider then the true shape of the distance, not a number on a chart. A separation that stretches from 35 million miles at its nearest to 250 million miles at its farthest. A gap so wide that a question sent toward Earth waits as long as half an hour for the beginning of a reply. The world that made you becomes a pale point of light hanging in a black, so complete it has no flaw and no edge. Everything you have ever loved is gathered onto that single point. Every face, every voice, every gravity your body was tuned to. And you are moving away from it, through a dark that does not know you are there and would not change if you were not. And yet, the body changes because the situation is unprecedented, and the mind changes because no one has ever been that far for that long. But change is not the same as ruin. The bone that thins can be measured, and what can be measured can someday be guarded. The brain that rearranges itself does so along laws we are only beginning to read, and laws once read can be answered. None of this is a wall, all of it is a price, and a price is a thing that can, in principle, be paid. The universe is indifferent to whether we go. It has set out no welcome and no prohibition. It has only set out the cost plainly in radiation and silence and time, and left the ledger open for anyone willing to sign it. That is the strange mercy buried inside the dread. Nothing about Mars forbids us. It merely asks more of us than any place we have ever gone. And it asks that price in the only currency that matters, which is the self that arrives not being the self that left. The first humans on Mars would not come home as travelers who went somewhere and returned. They would come home as people the journey had rewritten, carrying inside their cells and their bones and their sleep a permanent record of having been somewhere the Earth could not follow. That is not a failure of the mission. That is the mission. To send a part of ourselves so far that it comes back altered is the oldest thing our species has ever done. Only now the distance is measured in worlds. So the Earth made us, and the Earth will